It's a great pleasure. Go for it, Clem.
Okay. This is very fortuitous that I was asked to do this right now because just this year I had a publisher approach me about the calculus book that was out there and wasn't selling very well, and said we can do better and we'll be glad to take over the republication of your calculus book. And they are very aggressive. They made up a web page for me, and they made up a Facebook page, and they're, you know, creating a whole bunch. And they gave me a new cover, and this is it. And I took a couple of them and left them over at Mary's. So it's a better looking calculus book than last year. I mean, than 7 years ago. And not only that, I'm finishing a new book, which is called Equations, the Power and Beauty of Mathematics. And I just finished the 11th chapter of that book, and it's called The Calculus. And that book is about history and breakthroughs and stories about mathematics. Not all calculus. It's just just this one chapter, and then another chapter is on foundations, another chapter on linear programming, which is the same thing as operations research, and others on logic and a lot of other things. And last Friday I had the chance to read at the reading at the fireside, and I read the preface to that new book. And people were a little bit worried about a preface. The preface is usually the most boring part of the book. So I said, well, I'm going to read you the preface, and I could hear people saying, oh no, not the whole preface. And I said, yes, the whole preface, and I'm going to read you the preface from that. I made up a little sample copy of this book with the table of contents and stuff because I was promoting it at a book fair that I was in Florida. Here's the preface. I am mathematics. I rival music and painting and literature and poetry. My complexities and challenges define my culture, as rich and deep as any human endeavor, unveiling infinities beyond infinities, asking if truth and beauty can be found outside of my assumptions and beliefs. What happens if I assume such and such instead of so and so? Imagination begets creativity. Begets everything, including imaginary numbers. I am delighted when nature uses one of my answers. I can see connections that surprise all, except nature, of course. If you love mathematics, I needed to write you this book, to help you count the ways, to see how creativity conquers obstacles. But what am I to make of you who say you hate mathematics? I never heard you say you hate music, nor painting, nor literature, nor poetry. I needed to write you this book. You need to read this book. So it's a shorter preface than usual. Let's see how many. Well, I have 10 handouts, but I see there's more than 10 people here.
We can share.
Okay, you could share some. Okay. Before I hand them out to you, let me just start off with what I have in this chapter, and that is that I'll just start reading you the first couple of lines. In plein air is something artists, especially painters, do fresh and spontaneously. Mathematicians do something like this when they use calculus to solve a problem dealing with instantaneous changes in force, velocity, and direction. An outfielder in baseball does the same thing, watching the trajectory of a fly ball and adjusting his or her own path just in time to arrive at the right spot at the right time. Apparently, other living creatures behave in the same kinesthetic dance we call calculus. So that's my first definition of calculus. And I'm going to follow it up with a couple of problems that are quite interesting problems to illustrate. This is the last one.
Here.
Oh, okay. I do that. Okay. And you will see the first question in the next section is, do animals use calculus? And of course I'm including humans as animals, so yes, we do. But what about dogs and worms? There was an experiment done in 2008 by a University of Oregon biologist who set up a food source and had a group of worms that were going after the food source. And then he switched it to another location and intensified the odor, and the worms changed their path and went to that other source. And he was claiming that in their little brains they did a derivative, meaning they did a change. They calculated that something had changed, and so they were going to change their path and go towards that food. And my argument is, okay, that's a good model for a calculus problem, but mindless steel balls will do the same thing if instead of a food source you have a magnet. And if you intensify the magnet and switch it, the balls which were going one way switched and would go to the other magnet. So that, you know, I don't believe that the worm's brains calculated the derivative. But this one about the dog is really interesting. There's a dog, the man in Michigan who went to one of the Great Lakes and would throw a tennis ball from spot A out into the water, and his dog was there with him. And the dog would run. He would not jump into the water and swim towards the tennis ball because in the first place he didn't like swimming as much as running, and he couldn't swim as fast as he could run. So he threw the ball to a point somewhere C in the water, and the dog took off running on the land because he was sort of running towards where the ball was going. And then at the appropriate spot, at a spot you could find by using calculus, he jumped in the water and swam for the ball. What he was doing was finding the shortest time to the ball, not the shortest distance. The shortest distance is this. But he jumped in at a point, and when you calculate the calculus problem, which would minimize the time because he takes some time running, some time swimming. So the question is, how did the dog do that? Well, we'll see, but this is a problem that comes up in calculus because if you know the formula for rate is distance divided by time. Then you have the formula that time is distance divided by rate. By the way, the hardest part of calculus is algebra. If you can do the algebra, the calculus is really simple by comparison. So I have in here that there's two different times that if you look on page 325, there's two different times that are taking place here. One is the running time, and the distance that he ran divided by the rate at which he runs it gives you the time it takes running. And this point D is variable. It can be wherever it's supposed to be in terms of solving the problem. And the other time is the swimming time, and that's the distance that he swims divided by how fast he can swim. And it turns out that he can swim about 1/3 or 1/3.25 times as fast as he can run. So he can run faster than he can swim. So what you do is you calculate whatever x is. It's unknown. In other words, you have an unknown time that he's going to be running and an unknown time that he's going to be swimming. So he runs a certain distance. You convert that to time according to his rate of running, and he swims a certain distance, and you convert that to time. So the whole problem is rewritten in terms of time. So the time it takes to run any distance along the edge of the beach is the distance divided by the time, by how fast he can run. And the time it takes him to swim is the distance he has to swim divided by how fast he can swim. Well, when you calculate what y is relative to x, because this is a right-angled triangle, so if he uses up x time running, there's still 100 minus x time left that he hasn't run. And the place the ball went, say, is 50 feet into the lake. So this is really a function of x. In other words, the Pythagorean theorem tells you that the square of this is equal to the square of this plus the square of that. So y is the square root of the square of this plus the square of that. So you convert the equation into x's, and then you convert all the x's into time. So that's the algebra part. It's not even calculus yet. And that's why I say that's harder than the calculus, because what you're doing is setting up a problem to be one that you can work with calculus, but it's mainly an algebra problem. So on the next page, if you look, you see that the total time that he is running is the total time it takes to do the whole trip is running time plus swimming time. But both running time and swimming time are in terms of x. So the answer comes down to what should x be in order for the total running time and swimming time to be the least. So it's, and that's, so far we haven't used a bit of calculus. All we're doing is saying that's the algebra you need. If you're not good enough in algebra, you'll never be good enough in calculus, because it's just what it takes to do calculus. And so you'll see that we can write the total time then all in terms of x's. The only variable that counts here is x, because the running time and swimming time are constants. They're already fixed. And the relationship between y and x is the geometric relationship. If you drew a graph of that equation, if you look at it, equation 11.1, it's a square root equation. It's an equation x over 10, and then the square root of 100 minus x squared. So the graph of that actually looks like, well, it looks something like this. If you had a big enough graph, and with enough a scale fine enough, you could get exactly the lowest point of the graph by looking at it, by eyeballing it. And that would be the answer, and that you wouldn't need calculus at all. If you just say, I can find the lowest point of the graph by looking at it. And that's the application, the practical application. What calculus does is it gives you a formula for any equation like this that tells you what the slope of this graph is at every point. And so what you want to do is say, I want to find out where the slope of it is what?
0.
0. So I'm going to find the slope equation for this graph and then set it equal to 0, and that'll tell me what x makes the slope 0, and that tells me what x makes the point lowest. And you will find that the shortest possible time is something like 25.46 seconds. But if you look at the other approximation times, you'll see they're all around 26, 27. Good enough answers, actually. So the calculus is sort of superfluous here because even though it gave you the precise exact lowest moment for a problem like this, practically you don't really need to know that much. But anyway, that's the nature of how you would set up a calculus problem. And then I tried to ask myself how the dog solved the problem, and I just thought, probably like anybody else would, that he saw the ball going that way. He knew he'd rather run than swim, so he ran as fast as he could. Somewhere along the line, he realized the ball is getting further away, that he's not getting nearer, and that it's going more out towards the water. He said, okay, I'm going to jump in right here and take off after it. And then when this person did this experiment, several times he measured where the dog jumped into the water. He kept track of it. And it was pretty close to the calculus. So maybe the dog did calculus.
But he still hadn't proved whether or not that dog had any equations in its head.
No, you couldn't. I mean, I would be satisfied if the worms didn't, but the dog. I mean, the dog made a decision.
Yeah.
I don't know if you'd say the worms made a decision if they smelled the food. Maybe it is. It's a brain thing, so they must have made, something like a decision. Anyway, so the question that is, what is calculus? If it's something that can work problems like this, and it really is just a mathematics in which you work with what are called limits, that is, one variable approaching another variable, or one variable approaching a constant. And the word approaches is a kind of intuitive word, and it's not well defined. So if I told you, well, I wanted to find out what 1 over x minus 100 is when x approaches 100, I have to tell you what I mean by approaches, but you have an intuitive idea of what it is, and you can get by. You can do a lot of calculus with intuitive notions. You don't really need precise notions. And that's what Archimedes did. In 250 BCE, he calculated the area of circles. He did what is called squaring the circle. He figured out a way to make up a rectangle whose area was the same as the area of the circle to an approximation. Because in fact he invented the word pi, or the concept of pi, to say, well, that's the number you have to multiply by the square of the radius of a circle to get its area. And he actually he got pi by an interesting thing. He started off saying maybe pi is 4. That's not even as good as the Bible version of pi, which is 3. Then he said, okay, but I'm going to take away 1/3 of 4. So now pi is 4 minus 1 1/3, which makes it about 2 2/3, which is better than 4, but not very good. And it's under. So then he said, well, I'll add 1/5 of 4, and that gives me something back up as a 3, and maybe it's actually overestimate of pi. And he just did this alternating series of odds, reciprocals of odds. So if you take 1/7 of 4 away from that answer, you'll get closer to pi. And if you keep doing that, you'll oscillate back and forth above pi and below pi and so on. And that was very interesting for him to figure out how to do that, because later on, when calculus got developed well, there was something called the arctangent. The tangent of an angle is the height divided by the base here. You can write out a formula for the arctangent of a curve, which is it's still not calculus, it's analytic geometry, which draws the picture of the tangent. Either that way or that way. But if you expand the infinite series for the tangent, you'll get that it's something like, it's a reciprocal, it's like a series of x over 3 minus, x over 1 minus x over 3 plus x over 5 and so on. That's an infinite series for tangent. And if you look for the arctangent of 1, which is pi fourth, then you're saying pi fourth is this when x is 1. So pi over 4 is the oscillating or alternating series of reciprocals of odds. But Archimedes sort of figured that out ahead of time before calculus came along. He did a lot of stuff that he figured out ahead of time. In fact, there was something as recent as 2008 where they were able to devise a new X-ray technique for looking at the palimpsest, which was a book that had been written in in about 900, which was created by scraping off Archimedes' writings and turning the page sideways and writing prayers from the church. And so his writings are still there, but they were under the prayer book. And so it was finally they were able to X-ray it enough to find what he had written, and it's very good calculus. And that was in 250 BC he did that. Calculus was then invented later in 1670s, so quite a bit of time later. I'm not going to go through some of the details here, but the idea of verging, that's the word he used, or converging or approaching, is intuitive and not precise. But if you use inequalities, if you say, when you say close to, instead of saying close to, say less than a certain distance from, then you can introduce the concept of inequality. So you can say, if I expect this variable y to be close to, say, some number, I'm really saying I expect the variable y to be less than a certain distance from that number. And if I want to find out what it takes to say that y is approaching that number, I just have to say, what distance do I want, say, x to be from some number? Not just close to it, but, some prescribed distance. And will that assure me that I'll be that prescribed distance from y? It's a question of tolerance. I'm saying, if I want to meet a certain tolerance, what do I have to do to the variable that I am using to achieve that tolerance? And that's used instead of just getting close to it. Okay, now, what good is calculus? Well, if you go over to page 330, you'll see that if you're in physics, if you have a physics problem in which you're going to drop something and let it hit the ground, it's really not hitting, it's not just going to the surface of the earth, it's going to the center of the earth. When you drop something, if I had the earth drawn as a sphere, and I was right here, you could say, well, okay, I'm dropping it straight down. And if I'm here, I'm not dropping it straight down, but I'm dropping it straight down, meaning I'm really aiming for the center. So when you say straight down to the surface, you mean vertically to the surface, and then could be, from down here, it's down straight down. And the velocity of a body falling straight down is, because of the acceleration constant, is minus 32 times the time it's falling. And if you impart a little bit more velocity by throwing it down, then you're making it come down faster. Or if you reduce the velocity by throwing it up, then it has to overcome that in order to come down. So that equation would be minus 32t plus the initial velocity that you gave. Or if you just let it go, that v of not v naught would be 0. So you just have that falling body. If you want to know what the speed is at one time, like say the speed at 1 second, and then you're timing it on a stopwatch, and then what's its speed at 2 seconds, or let's say, other than just one part, say 5 seconds, then you would average the two speeds. You could say it has a certain speed at 1 second and a different speed at 5 seconds. It took 4 seconds for that speed to change, and just like you would do any kind of averaging. But what you need for a physics problem is not just the average speed, you need the instantaneous speed. You would need to know what happens if the time interval at which you're taking this average is 0. And you can't divide by 0. So what you do is you say, I want to find out what it was at one second and what it was at another second. And then I want to talk about what happens if I bring those two times together, and not actually put in a 0, but see what the whole formula looks like as you start bringing the times together. What happens generally, and this is a good part of the algebra for it, as soon as you set up that kind of average speed, you'll see something happen. There'll be a cancellation of that denominator. The denominator won't be there anymore, and you can let it be 0 if you want. I mean, you're not really letting it be 0, it's just not there anymore, and you can just plug in the last time and you'll get that. So that is called, the thing that's going to 0 in the bottom is called the indeterminacy. And the whole problem of differential calculus, first half calculus, is to set up problems and get rid of the indeterminacy. And that takes an algebra. What you're doing is you're just trying to figure out, wait, how can I make that denominator be canceled out before I let the two times come together. And that's all that's it. You don't have to do anything else in calculus. Finding the derivative of something, if you can set up the difference between the two values of the function divided by the difference in the two times, or the two values of the variable, and if you can get a cancellation, and so you won't have that denominator there anymore, then you can just plug in the final time, and you got what's called the derivative.
What about that guy Coriolis?
What's that?
What about that guy Coriolis and his Coriolis acceleration? Doesn't that complicates the problem?
Oh, I'm sorry, I didn't really catch me.
No, Coriolis acceleration.
Oh,
is the problem. Doesn't get where it's supposed to.
Oh, yeah, okay. Actually, just to illustrate the thing I just said about the derivative, if you look on page 335 at the graph 1113, the secant line, a line that cuts the two points of the graph. And on page 337, the tangent line, the line that touches the graph. It's the same graph. It's the square root graph. And in the first equation there, the 2 points are different. And if you find the slope is rise to run. It's the difference in how high the point is to how far away it is over to the x-axis. So the difference between the point B and the point A in height is the square root of t minus the square root of x. And the difference horizontally between the x values is t minus x. And you see that, say, on page 336, equation 11.9. That is the secant line, and that's the slope of the secant line. You can see there's a problem. If you try to let x equal to t right there, you'd get 0 on the bottom. So what you do is, this is algebra that is really the hardest part of calculus. Try to figure out a way, how am I going to get rid of that x minus t in the bottom? Well, you do manipulations, algebraic manipulations. And here, the simplest algebraic manipulation is to multiply the top and the bottom of that square root of x minus square root of t over x minus t by the square root of x plus the square root of t divided by the square root of x plus the square root of t. You're multiplying by 1. And it's okay to multiply anything by 1. You won't change it. But, well, I mean, you won't change its value. It's the same as it was before you multiplied by 1. But what you're doing is doing an algebraic manipulation, which, when you multiply those two top terms, the square root of x minus square root of t times square root of x plus square root of t, it comes out to be x minus t. And you just have to know the algebra for that. It's just the difference of two numbers times the sum of the two numbers is the difference of their squares. So that comes out to be x minus t. And now you've got a way to get rid of the indeterminacy, because you have an x minus t on the bottom. That goes away. You're home free. You've got the slope of the line joining those 2 points still, but no problem with letting the 2 points be the same. No problem with letting x be equal to t. And when you do that, that is, you let x approach t or t approach x, you get that the slope of the graph, then, the tangent line to the graph, is 1 over 2 times the square root of x, because you put in t there, you get x, and of course, square root of x plus the square root of x. Then you can answer all kinds of questions about it, like, will the slope of this radical square graph ever be 0? No, because there's no way 1 over 2 times the square root of x can ever be 0. There's no number you can put in for x that'll make it 0. Can you find where the slope is going to be, 5? Well, I just put in 1 over square root of 2. 2 times the square root of x is equal to 5, and then find out what x is. Or what will be the slope when x is 100? Well, you just plug in 100, and so you can find everything you want to know about this graph in terms of its slope from this formula, because you found the general formula for the slope of the line tangent to the graph. One kind of interesting question: does this graph have a slope or a slope at the origin? Well, it has a tangent at the origin, because the tangent is a line that just touches it in one place, and that's the y-axis. But that y-axis is a vertical line, and vertical lines don't have slope. So this does not have slope at the origin, but it has a tangent at the origin. And you can see also, maybe you can't see, but 1 over 2 times the square root of x being the slope at any point. If you try to make x get close to 0, then you're making the whole fraction blow up. Because if x is, say, 1/100th, then that's 1 over 2 times the square root of 1/100th, which is square root of 1, which is 1/10, and so you have 10 over 2, you have 5. And if you make it 1/10,000th, then you'll get, say, 50. And if you make it 1 millionth, then you'll get 500. In other words, as you get closer to the origin, then you can see that is what happens to that line. You take that tangent line and move the point A, and the tangent line starts going up towards being vertical. Okay, that's half of calculus. That's the first half. That's the half you had. Okay. And actually, here's a few more things. The actual derivative is defined, and you use different ways to represent the x's. You can have x plus delta x or x plus h or a whole bunch of things like that. But if you look on page 338, that is the actual definition of the derivative. That equation 11.12. That the derivative of f with respect to x is the limit as t approaches x of f of t minus f of x over t minus x. That's a slope equation where you're trying to make the denominator be closer and closer to 0. And then once you do that, then you can say, well, suppose f of x is any given thing, like say 5x squared. Well, you would just set up the algebra. The algebra is the hard part until you could cancel the indeterminacy. Or if you want to know the derivative of the sum of two functions, you would set up the algebra using that one definition. So I'm saying that's half of calculus because that's just finding derivatives. The other half is called integral calculus. And the way that you can think of that is what I have starting on page 341. Actually, going back to 340, you see other things that physics uses. They use a function of time showing a distance, that's displacement. A function of time showing the derivative of that displacement, meaning the rate at which the displacement changes over time is the velocity. Then the derivative of the velocity, that is how fast does the velocity change, is the acceleration. Actually, there's an engineering term for how fast acceleration changes called jerk. And you can imagine, if you're increasing the acceleration and all of a sudden you stop that increase or change the acceleration, you get a jerk, and that's an engineering term. The momentum of any of something is the mass times the velocity. That's really the mass times the derivative of the displacement. And the force is mass times the derivative of the velocity. That is, force is mass times acceleration. So force is mass times how fast you're changing the velocity. Force to leave the Earth, that is the force you need to send a rocket up, is mass squared times the derivative of the velocity if you're assuming a variable mass. Because when a rocket goes up, it's losing some of its fuel, it's losing weight. Its mass is diminishing. So you have either one of these two formulas. And all of those are really, they start off as algebra problems, but you can, grind out the calculus. And what you do is learn a bunch of calculus formulas, so you won't have to constantly derive them fresh every time. Once you learn the calculus formula, you apply it to there. And one of the interesting things in calculus is work. Work is force times distance. So if you have something like if you want to move the chair, then you have to know the force. Well, force is mass times acceleration. And then you move at a distance, and then that's distance times force, and that gives you the work you've done. And being cute here, one of the things about work, other than it being the curse of the drinking class, is that force is not always constant. So force might be like a rocket going, it's losing its fuel, or any number of ways you could say, suppose you're carrying something and somebody's dumping shovels of stuff on it as you carry it, then the mass is changing. And so it's not a constant force. The work changes because the mass is changing. If you just had a constant force, and I'm using a grocery cart, and you are pushing a grocery cart to your car, and it weighs 40 pounds, then you just multiply the force, 40 pounds, times the distance you've traveled to your car, and that gives you the work you've done. And if your car was 20 feet away, you did 800 foot-pounds. But suppose you had a leaky bag of flour in your cart. So you're pushing the cart to your car, and this is on page 343. You're losing a half a pound per foot leaking out, and so the mass is decreasing by half a pound every foot, and when you finish that and you calculate it as an approximation, you will get, instead of, this is the beginning of integrals, on page 344, instead of just a straight line across where with 40 pounds all the way for the whole 20 feet, you lose a half a pound in the, well, actually a pound in the first 2 feet, another pound in the second 2 feet, and so in the 20, I guess it's a half a pound, and so in the 20 feet you've lost 10 pounds. So you're down, your last push is a 30-pound cart. Actually, since this is a linear decrease, you could actually figure out the work you've done by just averaging the loss of 10 pounds. Just say you lost 5 pounds on average, and so you would end up figuring out that you have 35 pounds over 20 feet. That's 700 foot-pounds instead of the 800 foot-pounds that you had if you didn't lose any. But that's still an approximation. Actually, that is not too bad. But if you had a force which was a mass which was diminishing at other than a linear fashion, if it was diminishing, say, as a square or something, a square root, or even some oscillating things, then you would have a more difficult problem. In the approximation that we get with these big rectangles in figure 11.6, the approximation is better if you make skinnier rectangles and more of them. And so you get that the sum of all those skinnier rectangles gives you a better approximation to the actual work that you did. That carrying out that skinnying of the rectangle is another limit problem. You're trying to find what is the limit. If I keep making the subintervals at the bottom more and more smaller and smaller, taking them to 0, and increasing the number of them at the same time, you have a conflicting thing. You're getting more rectangles, but they're skinnier and skinnier. But they do have a limit, and that limit is actually the integral, what's called the integral of the curve. So you find that the actual work done finally, if you're desperate to know, is 700 foot-pounds. And that integral sign that you see on page 346, it represents, it's supposed to be an S, and it represents the limit of the summation sign. The big summation sign is the Greek letter sigma. So as you increase the number of subdivisions and decrease the size of the subdivision, in the limit you'll get the integral, which is called the integral from 0 to 20 of the function 40 minus x over 2 with respect to x. And the problem is you need to figure out how do you find that kind of an integral. Well, it turns out, and this is the sort of fundamental theorem of calculus, it turns out that when you find the function that is the integral of this function here, then you found a function whose derivative is this function. It's called, the integral is an antiderivative of a function. And that's sort of the big surprise at the end of the calculus class, that you've been working with derivatives, these ratios of differences, and then you've been working with sums which is the integral, which is sums of products. And it turns out that the sums of products is the inverse function of the ratio of derivative of difference. And here's one little neat way to show that. If you look on page 348, if you say that the area under a curve up to a certain point is A of t, say up until point t, in 11.9 there, A of t is area from the small a to t, and the capital A of t. And then the area from the small a to s is capital A of s, and then the area between them then is the difference between finding the area all the way out to t or finding the area all the way out to s. And so you've got now the difference A of s minus A of t. That is an area of that sort of not rectangle, but something that has three straight sides and a curved side. Well, anything that has an area, if you know the base of it, you can find its height. If I know the area of something, and I know, basically, if I know one side, let's suppose I had something like this, and I knew, let's just take the top half of that. Suppose I knew the area of this thing, and I knew this length here was 10, then area divided by 10 would give me the height, because not only is this area the area of that thing, but it's also the area of 10 times something. It's actually, there is actually a rectangle right here someplace whose area is the same as that squiggly thing. So it's just, I mean, suppose you had something like this, and you knew its area was, say, 50, and this was 10, then you know there's a height in here somewhere, 5, which gives you a rectangle. Well, that's not a good example. Let's say down here. It gives you a rectangle that's partially inside, partially outside of this squiggly thing, and it's not a good drawing of it. But anyway, the idea is that you can actually reproduce the area in a rectangle that's equivalent to the area that's under that curve. And when you do that, okay, I'll show you that on the next page. You have the area of that piece in between, A of s minus A of t. And you have a height that you get, go up to equation 16 there. The area divided by the base of the height. You have the area of that little piece divided by the distance between the t and the s. And that gives you the height. Well, what you should be looking at there is that A of s minus A of t over s minus t looks like the slope of something. We're just the same form as the slope of a curve. The difference in the two y values divided by the difference in the two x values. That h then is halfway between the upper part, that is the f of t, the larger part, and the lower part, the f of s, which is the smaller part. And just intuitively, again, you can actually prove this rigorously, but intuitively you ask the question, what happens if I let s approach t? So I'm looking at the equation at the top of page 350, the inequality at the top of page 350. Okay, if s approaches t, nothing happens to t. It's sitting there. I mean, the s is a variable that's moving, so f of t stays f of t. And if s approaches t, that a of s minus a of t over s minus t is actually the setup for a derivative. So when s approaches t, that approaches the derivative of a of t. And the bottom, the last thing is if s approaches t, f of s approaches f of t. So what you're saying is that the area, the difference in two areas divided by that difference of the base approaches the abscissa, or the height of the function. That means that the derivative of the area is the function. So this function, whatever it was, you took its derivative, and the area is the integral, because we just got through adding up all the rectangles and so on. So that's the fundamental theorem of calculus, that the derivative of the integral of a function is the function. And that's pretty neat. Then once you know that, then all you have to do is figure out how can I find a function doing the opposite of finding a derivative. If I have a function like this, for example, on page 351, like 0.06 x squared minus 0.001 x cubed, I want to find a function whose derivative is that. Well, if you know enough derivatives, and you have to know a lot of derivatives in order to solve problems like this. If you know enough derivatives, then you can say, well, okay, the x squared is the derivative of x cubed divided by a constant, divided by 3. And the derivative, and the function x cubed is the derivative of x to the fourth divided by 4. So I'll just replace x squared by x cubed divided by 3, and x to the fourth, x cubed by x to the fourth divided by 4. And then I'll evaluate that at the upper and lower points of the integral and get what the area is in terms of the t. And then for any particular number, you can find that. That's the whole calculus course in an hour. Maybe you know a little bit more than you knew about calculus, unless you already knew a lot about calculus and you don't. Any questions?
So what other disciplines are you, mathematical disciplines are you covering in the book?
I'm covering linear programming, which is called operations research, and I show how to maximize, like say in a city council problem, how to maximize the city's tourist score based on how many policemen or how many recreational systems they have. Or I have a game theory problem that shows if a girl is going out of high school and she wants to pick a college that is strong in math, art, or science, or music, or something, that she can make up a game and select one of them according to something that optimizes her goal. I have some of the history of number theory, of some of the solutions to the prime number problems that are in existence. There's one story in there about a man who was he was born in China and took college, went up through college in China, then he came over and got a PhD at Princeton. And he was really not a very good speaker. His accent was pretty heavy, so he had a hard time finding a job. But he got a job at the University of New Hampshire, which is not the world's top college or the nation's top college. Anyway, so he was working there as an adjunct faculty. He didn't really have a full-time job. He was making sandwiches at Subway to augment his income. But he figured out a problem which nobody had ever figured out before, and that is that there is a constant gap between primes. There's gap between primes. There's sometimes there's two primes in which there's no prime between. So he figured out that there was a gap of 70 million between two primes. nobody's ever figured out that there was a finite gap between two primes. So he got a job at Harvard, and everybody wanted, he ended up at, in California, Santa Barbara or something, no. I don't know, some university. But a team of mathematicians, a lot of stuff is done by teams, but he did this on his own. The team of mathematicians took his method and narrowed it to 1,030 or something, saying that there's a gap of that there's primes that with that gap. And then they kept going further, and so it's down to about 680 or something right now. From 70 million, I mean, that was how he figured out that there were infinitely many primes that were 70 million apart. And now they know that there's infinitely many primes that are 630 apart or something. So his is a real success story. And there were a few other, I have some other stories like that in there about spectacular breakthroughs. The theme of the book is mathematics is a problem-solving entity. And that's all mathematics. Every time that solves some problem, a new one comes along, and the effort is to solve that one. And so new problems are created by physics, biology, environment, economics.
So how often does it work the other way? How often does the mathematics precede the problem? In other words, the mathematics is out there, and then somebody comes along and says, oh, I can use that.
That actually happened a couple of times. Like there were a couple of young French and Norwegian mathematicians in the middle 1800s who it was Galois, Évariste Galois. He was trying to show how to solve fifth-degree equations. You can get formulas for fifth-degree equations. And he realized that you couldn't do it, and nobody had been able to do it. And then he proved that not only couldn't you do it, it couldn't be done. And he gave the conditions under which it can be done and which can't be done. And he was ready to publish that, and he sent it off and it got lost. And then later on, he had refined it and really wanted to get it published, but he got into a duel and was killed. But the night before, he knew he wasn't going to win that duel. It was over a political thing or something. He was 18. And so when and so that night he wrote out all the theory called group theory and gave it to a friend, and he was killed. And then about 100 years later, physicists looking for some way to explain quantum physics, it was group theory.
Yeah.
And so that was a case where the math was already there, waiting for somebody to find something good to do with it.
So I had a mathematician friend in college who was interested in math, and he basically said that to the physicists, so we just create things out there and then you make the world conform to them.
Oh, well, that's actually a back and forth, really.
Pardon?
It's back and forth. I mean, the physicists do glomp on to some mathematics, but then the mathematicians see what they've done with it and say, oh, that can lead to another development. One of the greatest mathematicians and she was in the 20th century, was Emmy Noether. And she had taken some group theory stuff, and she invented something called the Noetherian rings, which is used for physics to explain certain symmetries in physics. And she, her work was vital to some of the development of nuclear physics. She actually was teaching in Germany when Hitler came along and left. And Hilbert was one of the great mathematicians, David Hilbert of the early 1900s, would be teaching, and she didn't get any money for teaching, but she didn't actually have a position, but Hilbert would let her teach his classes because he was doing something else, and then he would pay her. And so but she never appeared in any of the catalogs as being the teacher. It was always Hilbert, but people knew which of Hilbert's classes she was teaching, and so they took his classes to get to be taught by her. And there were several great women mathematicians who ended up teaching under their father's names or under some other man's name. Actually, in the 1800s, mid-1800s, women weren't even allowed to go to university. There were a couple of women who went and finally got a hold of the teacher. There was a woman named Sonia Koblevsky who got a hold of Weierstrass, and he saw her and said, okay, work these problems, and he gave her a bunch of problems. He thought he'd never see her again, and she was back next week with all the problems solved and ready for some more. So he was astonished. There is a theorem called the Weierstrass-Kovalevsky theorem, but she was the one who made it up. Actually, her work was the basis for wave theory stuff, some wave theory theorems that was used to find the Higgs boson. So, and that the Higgs was, the God part that gives mass to particles.
Well, thank you very much, Clem. We got 1 o'clock. I don't know if we're smarter or not.
Clem, what is the publication date for your new book?
Well, I don't know. I haven't really got a publisher for that book. The calculus book is published and it's in the bookstore.
Okay.
The other one, I'm really happy with it because it does all the good stuff I want to do. But I don't have a publisher. I'm going to try to get a university publisher, so I'm going to contact some of the university publishers.
Thank you.
You can keep that if you have enough.